guys, to another session on CRC. This is one more attempt from my side to explore the math and the understanding of how the CRC is constructed and how the serial equation is formed from just the simple division math. And once you understand the serial equation, then the question is how do you convert that into parallel to actually get some speed out of that? And then from there, there's many other things come out of that, like, just the 8-bit tables that we construct. How can we apply those tables to get even faster CRCs, like, 128 bits at a time, 64 bits at a time, and so on, wide computations that can speed up the calculation even further. And then from there, you could apply these ideas to embedded systems or FPGA designs and so on. So, with that background in mind, let's dive into how this works. So, the CRC is essentially a division operation. Put very simply, if you were to divide, if the message that you're sending, which looks like a very wide, uh, you know, set of zeros and ones, right? So if you think of that as a polynomial, just think of, it's polynomial is a fancy word, but essentially think of those bits. It may be hundreds of bits, but assume they were just one number. If they could represent one very large number, right? And on the divisor, or on the bottom half of the division, what's in the denominator is what is called the generator polynomial. And the generator polynomial is just another number, right? Assume that, these constants here are basically ones and zeros. There never be anything other than one and zero, right? So, so now if you were to divide this message by this generator polynomial, what remains is the CRC, okay? And there's a little bit more behind it, which I'll show you in a second. But essentially, that's if you were to walk away with one thing, remember that the CRC is a division operation. And when you take the message and you divide by the generator polynomial, what remains is the remainder, which is the CRC. Then the other thing I would like to explain or emphasize is that these ones and zeros, this is not just a simple long division, right? When I said it's a remainder of a division, it's not just a simple division. It's a division done over a Galois field, which is a special kind of arithmetic, or algebra, so that you can do things much easier. And it uses an XOR operation. So we'll look into that as we run through the long division. So essentially, let's now dive, with this background, let's dive into a very simple example. In this case, we have chosen just a 4-bit polynomial, and the remainder in this case would just be 3 bits, because if the fourth bit was 1, you could go one more time. So the the important thing to note here is when your generator polynomial or the divisor looks like 4 bits, the remainder is going to be 3 bits. So if you want to construct a CRC32 where you have 32 bits of remainder, this will look like a 33-bit divisor. So keep that in mind. Now in this example, we keep this as the message. So what's in black is the message polynomial, and what's in purple is essentially the extra 3 zeros that we pad. So remember that CRC is going to be 3 bits. So by convention, the way CRC works is the way you run this through the serial equation is that you append these 3 zeros, and then you will compute the CRC. And these 3 zeros essentially just make sure that every bit is used. Every bit is pushed through this division problem, right? So if you put these 3 zeros, then everything is consumed. So you add 3 extra zeros because, like I said, these three, the CRC would be 3 bits in length when you have the generator polynomial like this. And then you append this at the end, and it ensures that every bit is consumed. Now, let's move forward with this. Let's do the very first one. So the way long division works is that if this MSB goes here, And if this is a 1, right, because this is always going to be 1, the highest bit in the divisor by definition is going to be a 1. So if when you put this along, when you align with this and say this is 1, if this was a 1, then you could actually XOR this. And I say XOR, but normally when you do division, you're going to subtract it. So the whole thing is that in this case, we use this algebra over a Galois field of GF2, which is, the only numbers it uses is zeros and ones. And the addition operation is defined like this. If you add 1 plus 0, it's going to be 1. If you add 1 plus 1, it's going to be 0. 0 plus 1, 1, and 0 plus 0, 0. So this is an XOR operation. Now, note that in this XOR operation, if you add 1 to 1, it becomes a 0, which means that the additive inverse of 1 is 1. Because, think of it another way. This, whatever you sum to 1 makes it 0, then this thing must be the reverse of 1, or the inverse, additive inverse of 1. Likewise, 0 is also the additive inverse of 0, because if you add this number 0 to 0, you get a 0, right? So the equivalent example to understand this would be, let's say we are doing decimal math, and I would ask you, what number, if I add to 5, would make it 0? You would say minus 5. And so minus 5 is the inverse, additive inverse of 5. Likewise, in this case, apply the same logic. So we can say that the minus 1 is really 1, because minus 1, which is denoted as the inverse, additive inverse, is really just 1, right? Plus 1 is the same as minus 1 in this math. And that is the magic of the using the Galois field, because this plus, which is really an XOR operation, the way we have defined it here, is really an XOR operation between bits. So if we can apply this XOR operation, the subtraction is really just the same as the addition. And so we will apply that property here. And now if you do this XOR operation, you get this. And so next, you're just going to do the regular long division kind of math. And then you get this number, you shift it left. Once you've XORed, you pop this, because this will always become 0. At this point, you can pop this off, right? And then so the remaining numbers that are there, you pull the next digit here, which is a 0, and then you try to XOR again with 1101, which was your divisor, right? And then you get something. And then you do it again, and this time also it goes, so you can XOR this. And then next time, and then next time, and the next time, till you're basically left with a 0 here and nothing else to carry it forward. At this point, there's no more digits left, and there's a 0 in the front. So whatever remains, we cannot do the XOR any more times, right? It's done. When the MSB is of the remainder, when the MSB becomes a 0 and there's no more digits left here, um, remember what I said in the beginning was that when you have 4 digits in your divisor polynomial, and then the CRC is going to be 3 digits. So there's nothing else to be done here, because this is a 0. So we have 3 digits left. We cannot bring any more digits in. So this 001 is the CRC. Now another thing I would like to show is that if you run this math, putting the 001 here, instead of 000, if you were to put 001 here, right? Replace those 3 zeros with a 1, and now run this whole division algorithm again, what you would end up getting here is a 000. So that is how you could actually validate the CRC. That, instead of checking it, what you could also do is just take the CRC as a part of the message, and then compute the digest, compute the CRC, the remainder over the whole thing. And if you do that, if the CRC is correct, then you would get 000. The resultant would be all zeros, because it's a completely divisible at that point, right? So that's uh, what the uh, division looks like. Now, from a division to generating a LFSR kind of feedback model, how do we do that? So the way we do that is that if you look at what we are actually doing, we have a divisor polynomial that we keep XORing into the numbers, right? And we always check if the remainder of whatever we are using, if the MSB is a 1, then we XOR and left shift, right? Look at it here. We XOR this divisor, and after XORing, this bit always becomes 0, so we remove it. And we start looking at the next 4 digits, right? And then we start XORing this again, 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 and so on. So that was one thing. If the MSB was a 1, then you XOR and left shift. If the MSB was a 0, if the MSB happened to be a 0, which I guess happens maybe here, you see the MSB is a 0. So you basically don't XOR anything, you just left shift. You don't XOR anything. So this is essentially what is modeled in these three flops or LFSR representation. Now, keep in mind if 1101 is the equation, how come we are representing that as three flops and not four flops? So the way it happens is that you always put one less flop because the output of this, if you assume this is the one that is going back that we check at the MSB is 1, and that is when we XOR, and we XOR this 1101. So this becomes the 1 that goes here, and then 1 and 0 and 1. The last one is basically XORing with the data input. Now, how is this true? So if you look at the remainder here, 0100, right? So 0100 is the remainder of this, and then basically you have left shifted it and you have brought in this 0. Now you're ready to either XOR or just shift. Now you will check of these 4 digits. So you pulled in the next data bit, and so assume that this data bit is the next bit, right? Because you have 3 digits. So if you look back here, what you would get at the end of the previous step, you would get these 3 bits, and then you're going to pull in the next here, right? And when you pull in this next, it becomes 4. So hence, you take the 3 bits of the CRC, you pull in the fourth bit, and that makes the 4 bits that is equal to the size of the divisor polynomial. So that's why you keep, these three flops, and you use the data in as your like virtual fourth flop, right? Because that will be pulled in when you look at it, these three were there and the fourth was pulled in. And when you XOR with 3 bits of this plus a fourth bit of data. That's how the division worked. Same thing here. So you have these three flops that represent the state of the CRC, and then the fourth bit, and then you XOR your 1101 on top of this. So you see this XOR is into this. So this will be XORed with, the 1. Um, and then this is, sorry, I'm sorry. This, so if you look at this, and this, what will happen is that this bit, so yeah, so if this bit is a 1, then you XOR 101 on the remaining. So the 101. If you look at it one more time, let's slow it down. So if this bit is a 1, right, which is this highest bit, if this is a 1, then what are you XORing with the remaining? The remaining is 101. You XOR 101 on the remaining bits, and then you will shift, right? So likewise, if this bit is a 1, then you will XOR on the lower 3 bits. You will XOR them with 101. So this bit XORed with 1, this with a 0, which just passes, and 101, right? So this then represents exactly this math here. It's an XOR operation, which is subtraction. Checks if this is 1, then you XOR the remaining 101 on it. This is exactly what this is. If this is a 1, then you XOR 101. And the last bit is actually the data input, like I described to you earlier. So spend a few minutes here and make sure that you understand that this is modeling this equation precisely, right? So this step here, if this was a 1, then you XORed 101 on the 3 bits below. If this was a 1, then you XORed 1, 0, 1, right? And you XORed them, and then you shifted it, because right after that, you'd basically throw away this bit, and those 3 bits would become the MSB, thus taking in the next data input. And so if this, when this shifts left, basically the next data input sits here, right? And this data input has been taken. So likewise, this data input was XORed, and then the next data input was pulled in here, and you're ready for the next operation. So that is then the serial equation that we needed to understand. Now, also understand that this could be written, because before we try to describe to you what CRC32 is, you must understand that 1101 can be represented as x to the power 0, x to the power 2, and x to the power 3, right? And we already said that the way you represent it is really these lower 3 flops. So instead of these 4 flops, we represented this like this. So if you look at CRC32, x power 32 is always 1, right? That's how this happens. This bit is always 1. But there, remember, there are 33 bits here, right? So likewise, this will be the x power 32, which is the 33rd bit. And then, you start here. You ignore this one because this is this feedback. And then x power 26, which would be, you have to put bit 31. This would represent 31, and then you so on and so on, and you go down to bit 26, and then you basically set the bit 26, right? So whatever comes into bit 26 would have an XOR of 1. Whatever comes into bit 23 would have an XOR of 1, right? So because why is that? Because if you look at this, this is bit 2, right? 2, 1, 0. And so whatever is coming into 2 is XORed with 1. Whatever is coming into bit 0 is XORed with 1. So follow the same approach. Whatever is coming into 26, C26 would have an XOR of 1. Whatever is coming to C23 would have an XOR of 1, and so on and so on. So now we have understood not only how to apply this very simple 3-bit CRC into 32-bit CRC, right? So we've gone from this step to this step. Now I want to show you, now that we have taken this step to understand how the serial CRC can be formed and extend it to a 32-bit CRC, let's try to extend this to something more advanced. And the more advanced is, how can we create a parallel table from a serial equation, right? The serial equation is clearly written here, right? And if I want to do the computation 8 bits at a time, then how do you do that? So the way you do that is that you apply this equation 8 times, right? If you have 8 bits given, you can apply this equation again and again and again and evolve that CRC into whatever would be resultant at the end of 8 bits, right? So that's as simple as that. Now, there's a couple of caveats here. CRC is not that straightforward because CRC always has a state. And the state of the previous CRC will always affect the net CRC when you feed in the next data. The previous byte CRC is affecting. That's the whole point of CRC, is that it is over the whole message, and therefore it affects the state of the message. The state of the message affects the value of the CRC at the end of the byte. If the byte was after 01, it would be a different CRC. If the byte was following 02, it would be a different CRC, and so on. So the way the table is constructed, however, is that you just assume the byte in isolation. So the CRC before this byte is 0. There is no state. Okay. And the state comes in later. When we try to understand how the state plays, you assume that the state is 0. CRC is 0. Just start from 0 and let's try to feed in those bits using some sort of equation like this. And this equation is described right here. So imagine you are applying this equation, right? So what you would do is that, first of all, CRC is 32-bit value. So you take in your byte, you left shift so that it aligns, because till these bits reach the top, remember the MSB has to be a 1. If this bit is sitting at the outside the CRC32 and trying to come into the CRC, basically the CRC would do nothing. So it'll basically just keep shifting up and up and up till the CRC has reached the byte has reached the MSB, and that's where the action will take place once the byte reaches the MSB. Now, by definition, CRC is only meaningful when that byte reaches the MSB of the CRC. Otherwise, it has no meaning. Because remember, the way CRC was defined was that you take a byte or a message and you left shift it by the number of bits that are there in the CRC, and you compute the serial equation over that message, right? So that the act of putting those extra bits at the back is basically this, that when you put those bits is equivalent of shifting it left by the remaining bits. So um, now we're going to apply this equation 8 times. And so every time what we'll check is if the MSB is set. If the MSB is set, then we will basically left shift by 1 and XOR with this polynomial. And remember, this polynomial, like we said earlier, you basically assume this is your polynomial. You ignore this MSB bit, right? You do not apply that MSB bit anymore. So the CRC polynomial, if you look at this CRC 32, you'd have to eliminate the 32, and the CRC polynomial will become this remainder value. So you keep XORing, you left shift if the MSB is 1, you XOR with polynomial and keep repeating it 8 times. And at the end of that, you would get the value for that specific number, right? And you iterate over all eight bit values, 0 to 255, and you would get your table. So now also in this equation is this case where if the MSB was 0, then you just simply shift it. And we remember this from our simple math was that, where the remainder was a 0, you simply did a shift. You didn't have to XOR it because it doesn't go. So you just shift it and then you keep moving on. That is basically oops, represented here in this equation. And now we have computed the tables, right? And now that you have tables, now we are ready to actually understand how to use the tables. So this is the final step. And in this step, multiple things will come in. There are multiple conventions that you have to understand to actually compute the classic CRC32. It's not really important from the understanding of the algorithm, and sometimes it gets in the way of understanding CRC itself. But let's see if we can explain some of those conventions to you. So one of the things that is there is that the starting value of CRC is FF, right? So that's 32 bits of ones. But when you feed your data, right? Remember that when you feed your data, let's go back to that very simple equation. If you feed your data and these were all ones, by the time this data gets to C2, these would have already XORed multiple times other bits and would have changed the state. So even though CRC assumes that all bits of CRC's initial state are set to ones, but it assumes no action is going to take place until unless these bytes, the first byte of data has actually reached the top bit, which means here. So no action is going to be performed. Okay, which all it means is that the initial data that comes in is basically XORed with this FF, so it's inverted. That's all it means. But if you get confused on this, it's probably much easier to understand if the initial value was 0 because no effect will happen till till the byte reaches the MSB, because when you feed back 0, it's going to do nothing. It's just going to left shift. So data is just going to get left shifted. So by that same convention, when they put these values to FF, all they did was that do not keep applying that XORing operation while the data is still entering the CRC register. Don't do that. Just assume that these FFs basically are just an XOR. So data just comes in, gets XORed with this FF, gets inverted, and that's where the first operation will start. So assume that the state is like this, and let's say you pick up the bytes, right? There's n bytes in your message. You pick the first byte, right? Then this other thing is that in CRC calculation, you reverse the bit order of the byte. So it's like a little endian mode of operations. So you basically take the byte and you reverse the order of those bytes, right? So take each byte, reverse its bits. Bit 0 becomes bit 7 becomes bit 0, and so on and so forth. Then what you do is that you take this byte and then you XOR it with the CRC's highest, which is the FF here, right? In the very beginning, it's FF. Later on, it'll change the state, and I'll show you with an example. So you basically have that byte, which we're going to compute, and so what you will do is that you compute whatever the byte was that you got in the data byte, you reverse it. Just by convention, you reverse it, or you could use it straight if you're just trying to learn it. But you reverse it, and then you take the highest byte, and you take that byte and you XOR this. This is what this is doing, is taking the highest byte, and you XOR this with your data byte. And then you compute the table over this, right? And then you XOR it by removing those CRCs. So there's two terms here, and I'll show you this in a second as to why this happens. But this is the magic. And in this slide, if there is any takeaway, it's this magic equation here, in which you compute the table over the MS byte XORed with the CRC's MSB, and then you left shift the CRC by 8 bits, and then you XOR these two. And that's really what you do over the whole message till this is all done. At the end of that, you just invert all the bits, and then you reverse the CRC to get the final CRC. But this is all just convention, and probably you can ignore it for now. The most important thing that happens here, the most important thing in terms of division and the actual math, which is very interesting, is happening right here. Okay, so in this example, let's take a very basic example where we are looking at CRC in the middle of computation somewhere. And the state of the CRC register before we try to compute on 0, 1, 0, 2, 0, 3, 0, 4 was already S1, S2, S3, S4. So in this state, how do we apply what we have learned going forward? We're going to apply this equation called CRC A plus B equals CRC A plus CRC B. And the way to apply this equation for the CRC computation is the following. This will also kind of show you how the table is used correctly. So the way you would apply it is that, remember, these bytes that haven't come in are really not that relevant. Till they reach the MSB, these bytes are basically just being shifted left and being XORed into the net result. So you could ignore the 0, 2, 0, 3, 0, 4 for now. Assume they're all zeros, right? It doesn't matter. Their values are irrelevant. What is material is the 0, 1 followed by, let's say, all zeros. We could just as well assume that. So we're just going to focus on that. And so if CRC of this plus this is really CRC of, we can only compute one byte at a time. And if you compute one byte, it's only going to be looking at this S1 and this 0, 1. So S1 plus 0, 1, this CRC is the 8-bit table that we just computed. So CRC of 8 bits, CRC 32 computed over 8 bits of S1 plus 0, 1, and this plus is really XOR operation. So if you do this, S1 XOR 0, 1, whatever this gives, this will give some value. But what happens to the S2, S3, S4? Because S2, S3, S4 has not really reached the MSB in this 8-bit operation feedback, this will just shift left. So S2, S3, S4, 0, 0 would be the net result because it's just left shifted by 8 bits. So what will happen is that this will net result into CRC of S1 plus 0, 1, S1 plus 0, 1, and the left shift of this, right? Which will, let's say, gives you M1, M2, M3, M4 is the net XOR operation. Now the state becomes M1, M2, M3, M4, and data is now left shifted by 1. So 0, 1 is gone, and 0, 2, 0, 3, 0, 4, 0, 0 is now your next thing. So apply the same logic. Ignore 0, 3, 0, 4, 0, 0, and assume that you have just 0, 2, 0, 0, 0, 0, 0, 0, right? So it'll do the same thing, CRC of M1 plus 0, 2, because those will be in 8-bit operation. You'll only chew through this 8 bits of this and 8 bits of this. Nothing else is relevant because it'll just left shift, right? It'll just simply left shift. So basically you compute the CRC 32 8-bit table of M1 XOR 02, and then M2, M3, M400, M2, M3, M400 is basically just a left shift operation. Let's say it gives N1, N2, N3, N4. So now you can see the pattern here, the way this forms. And if you go back now to look at our table, um, the way the table worked was exactly this. So CRC was left shifted by 8 bits, and the 8-bit table used had two things. It has two components, the byte that came in and the MSB of the CRC state, right? Those were XORed together and then the table lookup was made. Why is that being made is exactly shown here. CRC of A plus B, CRC of A plus CRC of B. So if the state, if you're operating only on an 8-bit table basis, you're only going to be able to see this S1 and this 01 of this sum, right? You're not going to be able to see this and this. This has no effect. It's basically just a left shift. So you might as well just left shift them and put them, like in this case, I mean, I'm doing this representative as S1, S2, S3, S4 left shifted, but I could also have shown you S1, S2, S3, S4 and 02, 03, 04, 00, both of these XORed because both of these components are just left shifts. The only effective component in an 8-bit CRC is this S1 and this 01, the MSB. So that's what is shown here. So hopefully this point is clear. Now we're going to take a realistic example. Let's say the state was 00 in the beginning. And again, the data, like we said, 01, 02, 03, 04. So let's operate on 01 first. If you look up the CRC table, um, the 8-bit CRC table that we were computing here in this step, right? And you can print these values. So what's going to happen is that CRC for 00 XOR 01 will be this. And then the remaining bits were 0, so that will be left shifted, it still remains 0. Now you're going to XOR these two, you're still going to get 04C1 1dB7. Okay. Next data bit is 02. If 02 comes in, it's going to be 04 XORed with 02, which is 06. If you take the CRC 8-bit table of 06, you're going to get this value, 1A864dB2. And then the left shifted version C1 1dB7, C1 1dB700 will be the other component. When you sum these two or XOR these two, you get this DB9B FAB2. And the next word will come in 03, right? And then 03 and DB will XOR together to, let's say, give you D8. And so you're going to do D8 CRC, which is this, and then the left shift 9B FAB2 00, right? And you're going to XOR these two and you're going to get the next one. AC691451, and then when 04 comes in, it'll be AC XORed with 04, which is A8, and then you do the CRC of A8, and then you left shift, which becomes 691451, 69145100. And then you XOR these two and you get this. So this will basically continue on till all the bytes were consumed, right? So in a sense, you can see this, that the way we did this equation was this equation is showing you how this works, and it's implemented right here. And you can see why this happens like this. So this step was essentially the linchpin of this whole solution, is understanding that CRC of A plus B, and then these S2, S3, S4 or 02, 03, 04 have very little value in this 8-bit computation. Remember that, because they just simply left shift, and you could do it many different ways, but it's essentially just S2, S3, S4 have no interesting work in this 8-bit CRC lookup over this whole bunch of bytes. The only bytes that have an impact is S1 and 01, because those are the ones that, as the 8 bits are shifted, those are the ones that will be checked for MSB of 1, and then the XOR will happen. So we basically treat them special by looking CRC only for them. The remaining are just basically just shifting left. So they are not treated any special. We don't have to do table lookups on this. It is just left shift. Gives you this value, and then we repeat the process over and over. So the way I would recommend you do is that the table that I've shown you, this table, you can print the values here, and then you can basically try to run through your program and print the byte by byte CRC, and you can do some of these steps by hand. Another thing I would like to recommend is that you could probably go back to this very basic equation and try to compute the CRC using this equation, right? This is also a fairly interesting equation because it's serial and you can understand this. And another thing I would like you to remind you is that, going to the very basics, remember that CRC of a message, if you are trying to use serial equation, is basically you have to pad with the number of bits of CRC in there at the end. If you don't do this, all the bits are not going to be consumed in the serial equation and you'd get the wrong answer because the whole division hasn't taken place yet. So the whole point of this exercise is to remember that CRC is just a division operation, and we went from a simple long division operation to realize that CRC is essentially nothing more than this LFSR feedback equation. Once we understood this equation, then we essentially knew how to convert this equation into this parallel form and create a table of 8-bit values. Then, using another interesting equation, CRC of A plus B is equal to CRC of A plus CRC of B, we can now understand that CRC can further be broken down and the table can be applied to continuously accelerate the calculation of CRC. It no longer has to be done on a bit by bit basis. It can be done on a byte by byte basis. And then I can show you in maybe another following episode how to apply this to even faster. You could do it on a word basis. You could do it on 64 bits. You can do it on 128 bits byte at a time. It's a bit more complicated and involved math, and it may require more tables to be created, not just one table, which is just a CRC 8, 32-bit CRC over, processing over 8 bits at a time. The tables have to be much more, and they're more complicated because you need to keep multiple states, and the math becomes a little bit more involved. But that's for another episode. And in this episode, if you were able to follow the CRC equations this far, then you can basically try this on your own and try to see if you can come up with the basic arithmetic, or I would say Galois field math, um, that uses the long division operation, come up to this point where you can translate that long division into this LFSR equation. And then from this LFSR equation, if you can get into this table and understand the math behind the table and understand this step here, this step here is really the crux of this acceleration possibility here. So hopefully, you enjoyed this video. I am trying my best to make it simple enough where you can see the magic pieces or the difficult to understand pieces where they are. I could try to make it in a bite-sized proportion so that you can easily go over them again and again till you digest them. And once you get it, once you've had the aha moment, then it becomes straightforward from that point onwards. So thanks a lot for watching this video with me, guys, and I will see you in another episode sometime. Until then, take care and bye bye.